Hey there, awesome physics students. Let's talk about parallel plate capacitors. It's such a useful and important example that we should spend a little bit of time with it. Here I've drawn a parallel plate capacitor so you can get a picture. The difference in voltage between the two plates is delta V. The physical separation of the two parallel plates is D. That's going to be in meters. And then the electric field between the two plates is E. And if you look up in a book, you can find another expression for E in terms of the charge that's on the plates and this constant epsilon naught and the area of the plates. And so this Q charge is the charge on the top plate. This epsilon naught is just a constant, and A is just the area of one of the plates. Okay? You'll notice that the electric field does not depend on the distance between the two plates. Now, my ultimate goal here is to find the capacitance Q over V for this configuration and try and understand it, see if it makes sense. So let's start with this. I need an expression for V. So how does V depend on the voltage difference between these two plates depend on the electric field? Well, the electric field, you'll recall, is the voltage difference divided by the spacing. And so that's telling you how the voltage changes as you change position. But the spacing is just D, right? So delta V, this is delta V over D, or in other words, if I multiply both sides by D to find delta V, that's going to be E times D, or ED, right, Ed? And so let's think about it if this makes sense. Electric field has units of volts per meter. D has units of meters, and so this is going to cancel and give me units of volts. So that's exactly what I want. Okay. That also reminds you why the units of volts per meter for electric field are very useful in reminding you what to do. Okay, so now I know V, but I want to put it in terms of this stuff here. So let me just write the delta V between the two plates is Q times D over epsilon naught A. I'm going to take that and put that down in here. And so I think we're ready. Capacitance is just Q, the Q that I put on the plates, divided by V. The V is the delta V between the two plates. That's QD over epsilon naught A. All right, so I think we're ready to look at this a little more detail here. First of all, I know that I can cancel the Q's, as I should. It should not depend on Q or V. It only depend on the geometry of the situation. Now, the other thing I notice is I have a fraction underneath a fraction. I don't like that, so I'm going to defractionize it a little bit. And so see if I'm going to invert this and multiply. So this gives me epsilon naught A over, and I just have D on the bottom. Okay, so now I can look at this. Again, this doesn't depend on the Q or the charge or the voltage. It does depend on the geometry, though, and I said that before, but what the heck does that mean? Well, it means it only depends on things like, well, forget about epsilon naught for right now. Depending on the geometry means it only depends on things like the area of the plates, for example, which it does, or the spacing of the plates. That's also the geometry. And so it does depend on the geometry, and so that's what I expected. Now let's see if it makes sense that the way it depends on those two. So first of all, I notice that if I increase the area of the plates, then the capacitance will increase. Let's see, does that make sense to me? Well, if I increase the area of the plates, then there's more places to put charge, and so I can increase the charge without changing the voltage. And so that does seem like that would make sense. There's more places to put the charge. There's more surface area to store the charge. I also notice that as I decrease the spacing of the plates, that also increases the capacitance. And that one's a little more confusing. One thing is to note is that the electric field here does not depend on the distance. So as I decrease the distance, the electric field doesn't change. Okay, that's strange. So the electric field doesn't change, but if I look at this, the electric field doesn't change, but the distance decreases. That means the voltage difference will decrease. And so if I look back at this, if I keep the same amount of charge on the plates, but I decrease the distance, that's going to decrease the voltage difference between the two plates. And if I decrease the bottom part of this fraction, that's going to cause the ratio Q over V to increase, which does make sense, okay? So these are some of the basics about parallel plate capacitors. And it seems like it depends on the geometry only, and the dependence does make some sense.